Hello everyone, myself Dr. Santanu Gundu. I welcome you all to this lecture of soft computing technique. This is the first lecture of module 7. So, in module 6, we have studied numerical example by using genetic algorithm. We basically solve few numericals by using genetic algorithm in the 6th module. In this module, we will try to understand the multi-objective optimizations. Basically, multi-objective optimization refers to the process of optimizing two or more conflicting objectives simultaneously. Unlike traditional optimization, where there is a single objective to optimize, that is maximize or minimize, multi-objective optimization seeks to find solutions that represent a trade-off between different objectives. Multi-objective optimization problems involve more than one objective function that are to be minimized or maximized. Answer is a set of solutions that define the best trade-off between competing objectives. So single objective optimization involves one objective function. That is, you can say that buy a house with a minimum cost. In multi-objective optimizations, problem involves more than one objective functions. Example is that buy a house with minimum cost but maximum comfort. Key concept of multi-objective optimizations. First one is the Pareto optimality. A solution is Pareto optimal if there is no other solution that improves one objective without worsening at least one other objective. This concept is central to multi-objective optimizations as it helps define a set of best trade-off solutions. A Pareto fund is the set of all Pareto optimal solutions. Objective conflicts in multi-objective problems, the objectives often conflict. In multi-objective problems, the objectives often conflict with each other. For instance, increasing the speed of a car might reduce its fuel efficiency, or increase the quality of a product might increase the cost. Trade-off. Multi-objective optimization involves balancing the trade-off between different objectives. In practice, this means identifying solution or improving one objective comes at the cost of worsening other. Solution set. Instead of a single optimal solutions, multi-objective optimization aims to find a set of solutions that represents various trade-offs between the objectives. Decision makers can choose from these solutions based on their preferences. Example of multi-objective optimization problems in engineering design. In a mechanical design, optimizing a car engine for both fuel efficiency and power output. In structural engineering, balancing the cost of materials and the strength of the structure. Finance and investment maximize returns while minimizing risks is a typical multi-objective optimal problems. Supply chain management, minimizing cost while maximizing customer satisfaction or delivery speed. Machine learning, balancing model accuracy and training time for minimizing error while reducing complexity. Environmental management, optimizing land use to maximize crop yield while minimizing environmental impact such as water uses or deforestation. Challenging challenges in multi-objective optimizations. Complexity. With more objectives, the problem becomes exponentially harder to solve. The space of solution grows rapidly. Pareto front analysis. Identifying the exact shape of the Pareto front can be difficult, especially in high-dimensional objective spaces. Preference attribution. When solving multi-objective optimization problems, there is often a need to incorporate the preference of the decision maker, which is subjective and might be hard to quantify. Applications of multi-objective optimization. Optimizing the design of aircraft for both performance and cost efficiency. Robotics, balancing the trade-off between speed, accuracy, and energy consumption. Urban planning, optimizing the use of land for housing, commerce, and green spaces. Healthcare, balancing the trade-off between treatment, effectiveness, and patient comfort. So, general form of multi-optimization problems, that is mathematically minimum or maximum fix. So I equal to maybe any number subject to jx greater than equal to 0, j equal to 1 to l and so on. Hkx equal to 0 where xi lies belongs to xi lower bound to xi upper bound. Dominance. In a single objective optimization problem, the superiority of the solution over other solution is easily determined by comparing their objective function values. In multi-objective optimization problem, the goodness of a solution is determined by the dominance. The definition of dominance. So that is dominance test. X1 dominance X2 if solution X1 is no worse than X2 in all objectives, and solution x1 is strictly better than x2 in at least one objectives. So we can say x1 dominates x2 or x2 is dominated by x1. We try to understand the example. Here, suppose there is four friends or a group of friends are going to take food at outside. So they'll always try to reduce the travel time from their home to a restaurant, and also try to reduce the uh, price of food. So their objective is that to minimize the travel time. So objective is to minimize the travel time, and second objective is that to minimize the price of food. Price of food. So there are six restaurants A, B, C. So there are five restaurants A, B, C, D, E. So travel time for the restaurant A is 100 minutes. For restaurant B is 90 minutes. For restaurant C is 80 minutes. For restaurant D is 75 minutes. For restaurant E it is the 100 times. So if there is single objective, travel time is least, then definitely the E will be the solutions. But here we need to look the other objective, that is the price of food. So price of food for restaurant A is 1600 rupees. For restaurant B it is 2100. For restaurant C it is 1900. For restaurant D it is 2400. For restaurant E it is 2250 rupees. So here if we compare the restaurant B and C, if you compare this B and C, see the travel time for B, if I write that BT, this is also greater than CT, and price BP is also greater than the price of CP. So in other words, we can say that C, the travel time for C is less than the travel time of BT, cost of C is less than the cost of B. So we can say here C dominates B, or B is dominated by C. Now if you compare the same thing for E and D and E. See, travel time is E for is less. Travel time for travel time of E is less than the travel time of D. Price also less. So we can say E is also dominated D. Okay, so E is also dominated. E dominates. E also dominates D, or D is dominated by E. So these are the examples. But if you compare the restaurant of C and D, so where the C travel time is less but cost is more, so they are not dominating each other. So this is the concept of dominant. Let's try to understand one more examples. So here examples are, we have plotted some 5 variables minimizing. There is some another example of dominance test. So that example 2 you can say. So there are solutions 1, 2, 3, 4, 5. So our aim is to maximize F1 and minimize F2. Okay, so maximize F1. So maximize F1 and minimize F2. So now here in the plot, this is 2 and 1. So 1, definitely the F of 1 is F of 1 is greater than F of 2. F1 is greater than F1 2. And also you can say that F1 is also less than F1. Okay, so F1 1. So for the case of 1, so F1 is maximized. If you compare between F1 and F2, so F1 is maximized. If comparing F2, so F2 need to be minimum. So here see the F1 is value is less of F1. Okay, so F1, so you can say that 1 dominates 2 or 2 is dominated by 1. So similarly, let's try to understand these things, that 5. So find the value of F1 5. So F1 5 and 1. So F1 5 is greater than F1 1. So if it is maximized, then that is better. Now you can say that F2 1, the value of F2 same height, so F2 1 is equal to F1 F2 5. So these are not odd-cell, so that also dominated. So here 1 dominated 2, because how 1 is dominates 2, because F1 is greater and F2 is less. Here in case of F1 is greater, so F1 1 is greater than F1 2, and F2 1 minimum is less than the F2 2. So that's why it is dominant. Similarly for this also, but 1 and 4, 1 and 4. So in terms of 1 and 4, so here you try to understand that F1 4 is greater than F1 1, and also F2 4 is greater than F2 1. So here it is maximized, but here it is not minimized. So here this is neither solution dominates. Okay, so I'll tell you later how to test these things. So please try to understand the definition of dominance. Now, Pareto optimal solutions. So given a set of solutions, the non-dominated solution set is a set of all the solutions that are not dominated by any member of the solution set. So the non-dominated set of the entire feasible decision space is called Pareto optimal set. The boundary defined by the set of all points mapped from the Pareto optimal set is called the Pareto optimal front. Basically, suppose this F1 is minimize, and also F2 minimize. Then suppose this is the solution space. So this solution is called the Pareto optimal font. This is known as Pareto optimal font. Pareto optimal front. Okay, this is known as the Pareto optimal front. So now try to understand the graphical depiction of the Pareto optimal solution. Suppose you are solving one questions which is that minimize F1, that represent something like cost. You have seen the example, minimize F2, that is also the time, you can say. So both are the minimum problem. So here this is the, you can say, F1, or you can say this is F2. Okay, so minimum cost and the travel time. This is travel time. So there is a number of solutions there. You plot the solution like this, like this, like this. Plot the solutions like this. Okay, different solution you plot. So both are the minimum. So the F1 is the minimum. So that is the minimum. Here F2 is also minimum. So this is the minimum. So this is known as the Pareto optimal form. Pareto optimal form. Another example, suppose we are maximizing F1, maximize F1 and minimize F2. So this will be the graph F1, so that is maximize, minimize F2. So if the solution space is like that, then Pareto optimal lies here. Minimize, maximize F1 and minimize F2. So there the Pareto optimal font, which lies in this region. Okay. So another example is that suppose minimize F1 and maximize. Let's see the previous example. This is maximize F1. So here minimize F1. So this is the F1 that should be minimized. So this side, maximize F2. So F2 is this side. So Pareto optimal is like this form. Then here the optimal font is like. So there is the, in this region you will get the Pareto optimal font. Pareto optimal font. So last thing is that maximize both. So maximize F1 and maximize F2. So both are maximum. So that is F1, this is F2. So in this region, Pareto optimal font will lie. So this region is the Pareto optimal font. So this is the Pareto optimal font. So we'll discuss in the future slides all these things. Second is that goals in multi-objective optimization. So find set of solution as close as possible to Pareto optimal font. And second is that to find a set of diverse as possible solution as. So as possible as solutions. So that is the basically here. This is the Pareto optimal font. So our solutions will be more close to the Pareto optimal font. So here more close and more diverse. So these two things. So that is more close as possible. This signify as close as possible. And this signify diverse set. So that is our goals in multi-objective optimizations. Now conclusion. So multi-objective optimizations is an essential field for real-world decision making where multiple conflicting goals need to be balanced. So various techniques exist for solving such problems, and understanding the Pareto form and trade-off between the objectives as crucial to arriving an optimal solution. So we have seen that the conflicting goals. Conflicting goals means something like I want to say that we want to maximize quality of some product. At the same time, we minimize the cost. So these are the conflict to each other. So multi-objective optimization is an essential field for real-world decision making where multiple conflict goals need to be balanced. Okay. So various techniques exist for